Excitation occurs if the bypassing electron transfers the right amount of energy to an orbiting electron to allow it to jump to a higher energy level. However, it still continues to orbit the atom and the change is only temporary. But if even more energy is transferred, such that it exceeds the binding energy of the orbiting electron, then it will be completely removed from orbit and you'll get an ion pair produced. Here we have an ion pair produced from an ionization interaction. The electron that is liberated from the atom, if it has enough energy, can itself fly off and cause other excitation and ionization reactions, and when it does this it's known as a delta ray. The further out from the nucleus you travel, the lower the binding energies, and therefore the easier it is to cause excitation and ionization. The loss of outer electrons also has less of an effect on the equilibrium of an ion than the loss of inner ones, as it causes smaller energy imbalances. To interact with inner shell electrons and cause ionization, more energy is required, as you need to first penetrate the negatively charged outer electron clouds, and then the electrons orbiting within these inner shells, such as the K and the L shell, will have higher binding energies which need to be overcome in order to cause ionization. If this can be done, however, then the resultant rearrangement of the electron shells in order to return back to equilibrium results in the production of characteristic radiation, which if it's in the right energy range can take the form of X-rays. I'll illustrate this using tungsten, which is a metal that's commonly used to produce X-rays, and in this example the high-speed electron is going to collide with a K-shell electron. If, via this interaction, enough energy is transferred to exceed the K-shell binding energy of 70 keV, then the electron will be ejected from its orbit and you'll be left with a K-shell vacancy. Again, the resultant ion is very unstable, as the outer electron shells have a full complement, while the K-shell is missing an electron. To become more stable, an electron drops down from the L shell into the space left by the K-shell electron, and in this form the ion is happier because it's closer to its equilibrium with a full inner shell. However, you've now moved an electron from a higher energy level, the L shell, to a lower energy level, the K shell, so there's excess energy that needs to be gotten rid of, which the ion does by emitting characteristic radiation, which is equal to the difference in the binding energies between the two electron shells. It's called characteristic radiation because it's specific to or characteristic of each element. So in tungsten, when electrons move between the L and the K shell, the X-rays released will always have an energy of 58 keV, and the same transition in a different element will produce characteristic radiation with different energy specific to it. X-ray production via characteristic radiation is the primary means of X-ray production used in mammography, and rather than tungsten, molybdenum is used to produce the X-rays.